this opportunity to speak with you. So first of all, a correction, my affiliation is not IIT Delhi, but IIIT Delhi, which is another university in Delhi. I am also associated with the Center of Excellence in Healthcare at IIIT Delhi and the Infosys Center for AI. So I'm primarily my expertise is in signal processing, and over years the signal processing community has moved to machine learning, deep learning areas. And I have been working in this, at least AI ML applied to healthcare applications since past more than 12 years. I'm working with a lot of hospitals in and around Delhi, and we get real data from different hospitals. If I summarize the current research in my lab, I can divide it into two parts. One is the methods. For example, we develop customized machine learning, deep learning architectures suited for the data that we receive from hospitals. The second bigger thread, now you know that we would like to deploy these models for in low resource settings in different hospitals, maybe in urban areas or the rural areas. So that implies that the model should be small so that it can be easily deployed. So we have been, of late we have started working on DL model compression and quantization, and of course agentic LLM. In the application domains, we are working in digital pathology. So for example, All India Institute of Medical Sciences, Delhi is one of the super specialty hospital, as well as sometimes we call it as a last referral spot in India. So we are working with them since past 12 years in the area of digital pathology. Particularly, we worked on blood cancers, B-type acute lymphocytic leukemia as well as multiple myeloma. Both are white blood cancer types. And we are now currently working with peripheral blood smear analysis and building our own completely customized software where we can integrate these tools. Cancer genomics is another bigger threat. So post lunch, I have a talk where I will show you how we developed a biomarker panel for multiple myeloma cancer. Now the idea is that being a MLDL specialist is really helpful, because that means that every type of data that you receive, whether it is a one-dimensional data, say speech data, audio data, ECG data or EEG data, you can analyze them, whether it is imaging related to natural images, or we say imaging related to X-rays, microscopy images, we can analyze those images. Likewise, even genomics data, we say that it is AGCT sequence, but the bigger point is how do you analyze these data. So in this talk, I'll be taking you through my journey of these 12 years analyzing different types of data, what challenges we face, and as an upcoming researcher, what are the things that you should be careful about while you build your AI ML models. So we worked on cancer genomics, then we also worked on cancer survival analysis and have deployed some models. I have deployed on my server and they are publicly available under the resources tab of my lab. You can actually put in the values and the model is running and you can take the inferencing from there. Cardiovascular disorders, this is another big threat for us. So three threads have become a bit bigger over these years. One is digital pathology, another is cardiovascular disorders, where we are now building again our customized multi-class, multi-label, big classifier model of more than 100 classes, where we are working with a lot of cardiologists in Delhi. Neuroscience also, because we have worked on fMRI, EEG, etc. I have graduated many PhD students in this area. And then conversational AI again goes back to EHR, etc. So I'll start with this. Why do we need digital technologies and what is the support there? So what are the challenges with current technologies? I think India and Nepal can share a lot of similarities, so you can better connect with me. Accessibility. is a bigger problem. Not every person in the country is able to access the technology when it comes to even healthcare. For example, people sitting in rural areas may not have access to the super special care when it comes to healthcare. Affordability is another big challenge. We know that our countries have a lot of population living in the rural areas. So even if I talk about India, the statistic says that more than 60% of the population is still accessing healthcare in the rural areas and not having access to the super specialized hospitals. Scalability is another big issue. If you say that for every disorder or every data analysis, an expert has to look at the volume of our population and the number of experts vis-a-vis that population, it's a bit of a challenge. So we say that if all these three becomes a problem, what is the outcome? Poor health index is the outcome, and we need to cope up with that. How do we do that? So digital solutions really offer a huge benefit. So digitization of workflow, if it is, we don't say that it is going to replace doctors anywhere, but we say that it is an aiding technology which would help support and bridge these gaps. So scalability can really solve the problem. So for example, I give you one simple example. During COVID, during the second wave of COVID, during first wave of COVID, India also survived very nicely. But during the second wave of COVID, we had a lot of mortality, and problems that happened was that most of the hospitals, even the specialists were not there. Who would handle the blood sample? Who would analyze it? Who would report from the pathology labs? Became a bigger trouble because even the doctors, nurses were down with COVID. And so if everyone has to see that, becomes a problem. But if there is a digitization of the workflow, we do have the solutions coming out. So scalability, we can scale up the solution. As a result of COVID, for example, AIM set up a fully robotic lab in NCI Jhajjar, where they have a fully robotic pipeline where the sample is connected, put over the conveyor belt, moves to the respective machines with the label identifies, the machines pick up, they analyze. And now if there is a complete digitization where the machines analyzes and also puts up report on the computer, so that means a pathologist sitting in the home, not seeing under the microscope, can look at it, re-annotate, rework on the report, and then sign off from there. See, the solutions become scalable. Reduced turnaround time, reduced cost per additional sample if the volumes are large, which is so, for example, in India. Improved diagnostic accuracy, but the moment we say improved diagnostic accuracy, at the same time it comes with the challenge. We see lot of AI ML models are coming in past 20 years or more than 20 years. So many people are working. How many times we say that those models are usable across hospitals? So if I give you one simple example, say MRI. So I have seen since years, lot of people are working in MRI domain, but when it comes to, we say that machine to machine variability is there. If it is captured with the machine which is 1.5 Tesla vis-a-vis 3 Tesla or vis-a-vis 7 Tesla, SNR varies, and now there is a challenge. Some person would have a different protocol where the size of the 3D volume would be different for one machine at another place. So then the challenge is that one model which is trained on one type of data, it's not deployable at every center, for every machine, everywhere. Right? So the challenge is that now, although we all are building models, we all are publishing papers, but when it comes to a deployable model, a usable model that can be used by anyone, it's still a larger challenge in almost all areas. So thanks to the LLM models that have come up now, we do see that at least technology to some extent, the MLDL, we are able to use it with a lot of good accuracies in many domains, but still that means in the specialized domains, niche domains, we still need to develop models that work irrespective of the machines, that work irrespective of the size. And so these days are emerging the concept of foundational models. So people are saying, let's build a foundational model maybe for MRI, let's build a foundational model for ECG that not only handles data of any type of collected from any device, any size, any duration, etc. And any disorder, multiple disorders, we should be able to build the model, train the model, but the challenge is that we need humongous amount of data. But this is where we are moving, that once we deploy the model on the prospective subjects, that is on the future collected subjects, the model should work with good accuracy, and only then we'll say it is indeed giving me an improved diagnostic accuracy, not before that. Before that, we are just saying it, but it's not happening. Ease of deployment, so we are now moving towards deployable, customized, smaller, compressed models, so that would also happen. Enhances early disease detection. Imagine that we have built a foundational model, a small model, we have also deployed on the cloud, or in a small, now you see that NVIDIA has those small cards, Jetson Nano, you can actually fuse the algorithm, put it on the small device and make it a portable machine, and that can also be deployed in the rural areas. So once that is done, that means that if you start doing mass screening, or maybe the screening on annual basis, if the cost per sample comes down, so, and if these models are built on all types of disorders of a particular modality type, so imagine what would happen, that early disease diagnosis would start happening, because the person went for the analysis of one single, but because the model is built up on number of disorders for that data, so that means it can start giving warnings that maybe it is also this disorder as well, which many a times it happens that the person doesn't know what all disorders he or she is carrying, and maybe that can be known early on. So that way it enhances early disease diagnosis, and then of course supports personalized treatment plans and research, and increase accessibility in rural and urban areas alike. So for example, if we look at the cancer statistics also, we see that Asia has high incidence of mortality, and even the predicted mortality rates until maybe 2035 are also very large. So we can see that until 2022, we had a huge number of deaths in millions compared to other regions, parts of the world, for example, Europe, Africa, etc. And now they are still projected to increase. The projected increase is also very large. So we really need to be taking care of these, or building these solutions and deploying those solutions. So one example, as I was giving example of COVID also, is for example digital pathology. So what is digital pathology? Implies that involves acquisition, management, sharing, interpretation of pathology information in digital environment, and the benefit that comes is that you can now mix multimodal data. So for example, imaging, molecular, genomic and other lab tests you can incorporate within your model and build the model that can handle this, and would really become very helpful. So what is the traditional pathology sort of a thing? Although, so we say that it's still the gold standard, that a pathologist under the microscope looks for number of cells. For example, for one particular blood disorder, maybe saying 100 cells I'll see, or 200 cells or 500 cells, and it's still considered as a gold standard. Although there are cell counters and different machines, but those are used to sign off reports when the person is normal, and those machines say that person is normal. The moment there is a flag that the person is abnormal, the pathologist then again comes and sees under the microscope, and that is the gold standard. Now, but the benefit now that has come up is that you have motorized microscope where it can automatically go to different fields of view, focuses, and so it's relatively easier and less time consuming to actually focus on regions of interest under the microscope on the slide, and then capture it, and you can also see on the bigger screen and then can sign off. But in digital pathology, we normally talk about whole slide scanners. So I'll give you one example of that also. But in modern healthcare, so for example, we say that the global digital pathology market is also expected to grow very rapidly. until 2032 to about $1.96 billions. And we can see that a big share has been captured by North America. So what was the sentiment on digital pathology post-COVID? It will replace a pathologist, early pre-COVID era. But post-COVID, now we say that most of the people would say that it will complement the work of pathologists and will actually aid them. And now no more the doctors are worried about, or they look at it that no, what is the solution, we don't care. Now most of the time when we collaborate with the doctors, they are really helpful and they come forward, they really want to participate in building the solutions. So one of the key thing that has come up in digital pathology is, for example, whole slide image scanning. So now look at the challenges that also come with the technology. So this is one microscopy image that you look at a slide under the microscope, focus on the region of interest where a cell of interest is lying and capture the image. The size of the image could be, say, 256 by 256, occupying only maybe 196 KB on the hard disk, to around 2040 to 15536, just some numbers that we have also captured a lot of data, around 10 MB of image. But look at the whole slide image scanning. It will actually scan the entire, if it is a 2.5 centimeter by 2.5 centimeter area on a slide, it will scan the entire thing, and the size could vary from 15 GB to maybe terabytes on a hard disk. So imagine the amount of data, massive amount of data that you have. Storage is a problem, processing is a problem, and to build the customized solution that will load this data and also analyze this data is also a problem. So we get the benefit that now no more the pathologist has to sit and maybe zoom on special areas and then scan it. What we can do is we can put the entire slide under the whole slide scanner. It will scan the entire area. We'll actually then we'll run the AI algorithm, cell localization or region localization, segmentation, classification, etc. Everything would be done. But then that means that we also need to handle this humongous amount of data that we are collecting at the same time. So this is one foundational model that came in Nature 2024. This is Providence Gigapixel Pathology Model. So what is meant by foundational model? I am again explaining. So for example, what they did was that they collected data from 28 different cancer centers. It was a data of around 31 major tissue types. So that means, see the kind of different types of cancers they must have collected. Of 30,000 patients it covered and had whole slide images of more than like 171, close to 0.2 million whole slide images. I showed you the size of one. So many images they collected, and then they pre-trained. They made patches, small patches of 256 by 256 patches, and they pre-trained this model on 1.3 billion such patches. So when we say when would a DL model will become deployable that works efficiently post-deployment, that means it needs to see the varied amount of data, a large amount of data, so that that it's almost seeing whatever is going to come in the future, and so that it also extracts the most relevant features out of the data and not giving you false predictions just by rote learning of the data, but by getting trained on that data. So they trained LongNet model, which was a big transformer model, and they used the vision transformer, took the image embedding from those patches, and then used this LongNet model along with this to train the network, and then came up with a digital pathology sort of foundational model. So they showed that out of 26 tasks, on 25 tasks, this model actually was beating the state of the art performance at that time. Now, what are the challenges that come with the images? So I'll also describe some other image data types. So some examples I've taken from digital pathology. So the bigger problem that would happen in digital pathology is, the first problem that you would encounter is stain color variations. So for example, look at this slide. All the three images are actually from breast cancer tissue, and you can see the color contrast is so varied for all the 6 images, right? They have been collected at different centers. So for example, Drexel University Cancer Genome Repository, UCSB Center, etc. So the color contrast is very different when you collect the data. And that means, so the moment you say that we are going to do localization, segmentation, and classification, maybe the texture becomes important when it comes to classification, but when it comes to segmentation and even localization, it's not just the texture of the object of interest, but it is also the color that is coming there. I give you another example. So for example, we collected data of bone marrow aspirate images or microscopy slides prepared from bone marrow aspirate and peripheral blood smear for multiple myeloma blood cancers. I told you about 2 blood cancers. So what happens is that they put a drop of blood or the bone marrow aspirate on the slide, then they put a staining chemical. And the purpose of the staining chemical is actually to enhance the cell of interest. So for example, if it is a white blood cancer, then they would like this staining chemical to get attached to the white blood cells, not to the RBCs, right? And then highlight those cells so that you can segment them. You can actually clearly see them under the microscope, so the pathologist can see them very clearly under the microscope. So the nucleus of the cell that you see here is the darker portion, and the cytoplasm, they actually stain with slightly different color. So these are mixed chemicals that you put, for example, H&E stain, that means hemotoxylin and eosin stained images. So they sort of capture slightly different color contrast. So that means that color contrast is really important, and we know that with which color the nucleus gets colored or stained, because it's basically a chemical that will get attached to the chemical which is there on the cell, or that liquid is also a chemical. So they get colored to that. Now if there is a color variation that happens because of different reasons, so that means that the performance of your algorithm will also vary. Maybe you collected data from one center or from during one time, and you say that I am training my localization, segmentation, classification algorithm on that. Now imagine after 2 years you collect the data, the chemical bottle actually changed, maybe it is coming from a different vendor now. Slight difference in the composition will actually change the color of that which gets stained, and now you suddenly find that the performance of your algorithm is not appropriate. We collected data over 2 years, and we realized that we are really finding lots of problems. That one time we tune the algorithm, it is working fine, but another time again it's giving a bit of a problem. So we sat with the pathologist to understand what it might be happening, and then they explained us the process of staining the whole thing. They said, so how it is happening, that you first of all, so from where all these stain color variations would come. So she said that we receive a batch of chemical bottles that we use to stain, and these chemicals, even though whatever temperature conditions we keep it, over time the chemical is also reacting within itself. So if I use this same staining chemical bottle, after maybe 2 months, I see a slight variation on the chemical, on the color contrast on the images. Then the second variation, she said, what if different technicians are using staining the slides. So maybe one technician would, although there are standard operating procedures, but would take slightly more time, soak it for slightly more time. It is like dyeing a cloth. If you put it more time into there, so you will find that it gets a stronger color. So that can also happen. can bring a change in the color. And then also because of the device and all those things. So we realize that means that there are number of reasons why this stain color variation is coming, even for one center, even for one lab. So what we did was that we developed an in-house pipeline where we identified 3 different types of reasons. So when they said that the color, maybe I put more color or keep it for more time, and that, so we said that means the quantity of stain absorbed is more. The first one, that there is a staining color variation because of the chemical. Then we said that what if I do the stain decomposition and say that there is a basis vectors which are actually capturing the different directions where the stain chemical is aligned, and the quantity that it is leaving at a pixel. So that means my vectors can also rotate. So that means that we connected the problem that they narrated with the kind of data that we get and how should we build the solution. So we actually moved from the RGB space to the optical density space using Beer-Embert law, and then did the stain color decomposition using SVD, and then aligned the vectors with the reference image vectors and did the quantity correction. So that means the technology can be very simple and it can connect to your basic math and whatever you do in your BTech, provided you understand and relate it back to what the problem is to be solved about. So that's why at times we say that if you're working in healthcare, lot of free data is available. But generally it is really good to sit down with the expert and understand how they are collecting the data, how they are building the data, and what could be the natural problems in the data, and how you should now build a customized solution. So most of the time what we find is that someone gives you the data, you say it's the data, I am the data expert, I don't care about rest of the things. I'll just take one, there are so many off the shelf model, let me pick something from the GitHub and then just throw my data in and take the results out and it will start working. No, it won't work. So that means that where you need a very small model, you're actually using a very large model, and that's not going to do a good job. It's better to connect with the problem statement, identify, look at your data multiple times, and then look for the solution. If there is no appropriate solution, build a small customized solution for your data. So then what are the other challenges we found? So stain color variation is one problem that we identified, but then there could be device effects also. So we actually over 2 years we collected data from 2 different microscopes, and we realized again there was a bit of a problem because the moment we change the microscope, then ambient conditions can also change. Sometimes I'm taking the pic when it is very bright in the room, and when it is not so much bright in the room, that is also making a change. Then scanning artifacts are there. I don't know how clearly you can see my images here on this, but there is one streak. So we saw that sometimes what happened, that the way images are made, there is one slide, glass slide over which you put the drop and then stain it, and again over it you put another small glass slide over that. Now sometimes that is a little bit broken, so that will give me a bit of some artifact which is actually not part of the data, but because my slide was broken or some streak was there, then maybe the way staining chemical was put, it was splattered over this slide. So there are some drops, some nodules, some drops which are actually not any cell, but because the staining chemical is scattered over it, that is also there, making it noisy. Sometimes, so from person to person, one person has focused precisely, another has not focused precisely. So not focused precisely, that means there is a slight blurring, very small amount of blurring, that is also there in the images. So if all these artifacts are there, and if you are the person who is building the solution, I would say, have you gone through the data? Every image that you're feeding to the training model? If yes, you know that if it is a DL model that you're building up, what kind of augmentations you should do. If blurring is my natural thing that is happening in the way data is being collected, then Gaussian blur is a natural augmentation that I should include in the augmentation itself, right? If my cells are circular or oval, that means I can do the rotations. That is a natural augmentation. So augmentations also become important provided you understand your data and the scanning artifacts you actually incorporate to your benefit, making that it should be part of my augmentation that also boost or increase the size of my data and make my algorithm robust to that, right? So scanning artifacts was another problem. Another problem was the challenges of the data. So we wanted to do, for example, when we wanted to do healthy cell versus cancer cell classification. Now, multiple cells, if you see, for example, the second tile, you can see here 2 cells are adjoined together. One may be a healthy cell, another may be a cancer cell. So I really need to segment them out and individually tag them whether it is a healthy cell or a cancer cell. But then it becomes a bigger issue because the cell could be joined together in multiple ways. And we found a lot of challenges with this data. So for example, 2 nucleus might be connected together where I need to segment it. Nucleus of one and site of another could be connected with each other. Maybe 3 cells are joined together, not just 2 or 3 or 4 cells in clusters. So particularly, so for example, if you look at this style, you can see lot of cells are together. See, it is so hard to separate them. So when it is the peripheral blood smear, the cells are isolated. But when it is bone marrow aspirate images, the cells are very strongly connected together and you can see lot of cells are overlapping over each other. So segmentation became a bigger problem here, particularly for multiple myeloma when we collected from bone marrow aspirate. So we also ran 2 international challenges, one in IEEE ISB 2021 and then in NeurIPS 22 was also, our data was part of one medical imaging challenge of this particular multiple myeloma type. So the data set itself can have a lot of its own challenges that make the problem difficult. Now another problem we found over time is the label noise. Now this is an interesting problem that we figured out. So I again tell you a story. So initially when we approached the hospital, we said that we want to do cancer versus healthy classification. On cell type, we can do that. They said, okay, fine, but the bigger problem is that under the microscope, both healthy cell as well as cancer cell, morphologically, at least for the blood cancer, they look alike. There is no difference. So now the pathologist is saying, oncopathologist, that even I cannot say under the microscope that it is a healthy cell or it is a cancer cell. How would you say? And so our next question was, then how are you diagnosing? So they're saying that initially when it is suspected that a patient walks into the clinic, clinician suspects that the person might be having blood cancer or this type of a cancer. They recommend the blood test. And now the slide is made and is seen under the microscope. So healthy patient or healthy person would have certain percentages of cells of every different types in the blood. When it is cancer, we know that it means unrestricted growth of one particular cell type, and that leads to the cancer. So suddenly they see, if they see that one cell type has increased hugely in number, when they see the slide under the microscope, they can immediately diagnose that this person is suffering with this cancer, and then they can go for more specialized test if needed. So that's the baseline. That is, once the day the diagnostic is being made, the patient has not been earlier diagnosed with that cancer. So far the story is good. Now when it becomes complicated, so now the chemo or the radio or whatever the therapy has started, and now the patient has started responding to the treatment. So the cells have now declined in the blood. So chemo becomes a bit of a problem. If it is a child or if it is an old person, sometimes it can become lethal if you give extra chemo. It's really difficult to survive. So that means that they need to take a call. So now is the enough chemo or therapy has happened, should we discharge the patient? So they look again to the data and they want to make a call, is there any residual disease left? Now this time, because the number of cells have declined to a great extent, they cannot see it under the microscope. What they do is they go to the advanced stage, which is flow cytometry or mass cytometry analysis, and there the tests are really costly and only the expert runs those machines. So then they confirm. So now at stake was that what if we help you with this analysis, looking at only the microscopic images, and we help you distinguish that this is a healthy cell, this is a cancer cell. So that means the technology would be way cheaper, and that means that it can be deployed in any pathology lab, not in the specialized centers where the cytometry machine, which is a costly machine, would be there, right? And any person can operate it. Now the bigger challenge was, how do we label the data? So whenever I am building a machine learning model, I need a ground truth. So ground truth means that I would ask the pathologist, put the label on that this is a healthy cell, this is a cancer cell, which the pathologist saying in the first meeting itself that under the microscope, when I look at the microscopy image, I cannot say which one is healthy, which one is cancer. I can identify the cell type that this is the plasma cell, this is a neutrophil, this is basophil, but I cannot figure out whether it is a healthy cell or a cancer cell. So then we came up with the strategy that the patient who is suffering with multiple myeloma at the baseline, every plasma cell in the slide will label as the cancer cell. The patient who is not suffering with multiple myeloma, whose blood slide was prepared due to some other reason, the plasma cells of that patient would be labeled as healthy cell. Now, can you imagine that there is a label noise in one type of cell, where the healthy cell is okay, every plasma cell would be healthy, would not be a cancer cell, but the cancer patient whose every plasma cell has been labeled as a cancer cell, maybe a little percentage of that would be of healthy cells, not all would be cancer cells. So we were careful in collecting the data that the patient which had full-blown cancer, we would still say that maybe 99% of the cells would be the cancer cells, maybe only 1% or maybe less than that would be healthy cells. But that means that label noise has creeped into the data the way we prepared the data. At least we could prepare the data, but then that means that there is a label noise when it comes to the classification. Not when it comes to the localization and segmentation of plasma cells, but when it comes to the classification. Now this label noise or ground truth labeling is sort of a bigger problem in medical domains. I'll also explain you when I come back to the future slides that it becomes a bit of a problem. Sometimes no one knows what is a ground truth, and you're still solving the problem. How do you solve the problem? So that means again it goes back to, do you connect with the domain? Do you connect with the application problem that you're solving? Don't solve it just as a data scientist, but solve it by connecting with the problem. Spend more time initially, maybe 1 month or 2 months to understand the problem, and then do the rest of the job. So label noise is how it creeped into, and we needed to then build the model that handles this label noise at the same time. Then the model should be generalizable on multiple data sets, should not only work on my. When we come up with the architecture, we say that we demonstrate the applicability or generalizability of the architecture, that it works on different types. So now, partially I answered what type of augmentations would work that are natural to the data that has been collected. So for example, here the blurring, so you can see that this data is actually from Chameleon 17 challenge, which ran on breast cancer slides labeled as whether it was a cancer pick or cancer or a healthy pick. And the data was actually collected from 5 different centers. So 10 WSI images, whole slide images, were collected at 5 different centers: C0, C1, C2, C3 and C4. So see, we made C3 as a reference, but you can see all the images are having different types of color contrast which are collected from different centers. So these are different images, C0, C1, C2, C4, again C0, C1, C2, C4. So you can see C2 has very different color contrast compared to C0 and so on. And so we considered C3 as a reference and then did the stain color normalization with our own in-house. These are the normalized images you can see look very similar to C3. But what kind of augmentations you would do? So for example, Gaussian blur, rotation, or maybe if there was staining chemical spillover over there, so maybe that sort of noise you can add to the images and so on. If it is, for example, ECG data, we generally say ECG data has baseline wander. I can add then baseline wander as a natural augmentation. Noise, somewhere spikes come, so I can add those kind of noise. So you should see different data requires different types of noise to be added as augmentation strategy. Now, is it necessary to have a complete MLDL workflow all the time? So for example, the kind of the stain color normalization we actually built, as I told you, that it was SVD decomposition, and then we built. So it was a complete mathematical formulation and a very small algorithm that implemented the whole thing with great perfection. We didn't need to do any MLDL here. So not everywhere you need to do MLDL, so you should also be able to take a call where you should be doing MLDL. So then when we were working on this paper, so we got the review comment that no, demonstrate with the method. What if it was completely MLDL workflow for classification or any task, downstream task? What if you had done those kinds of augmentations in the data itself and then build the pipeline? So what we did was that we took this public data set because so that we could demonstrate it on that, and we actually trained on the C3 data. We did everything on the C3 data, and we tested the algorithm, everything on the C0 to C4 data. So we took SqueezeNet, which was pre-trained on ImageNet data, and we did stain color normalization using our pipeline of normalization on C3, considering C3 as a reference, and then just did the classification on this. Vis-a-vis, we also had an architecture where we didn't do the normalization of images using our method, but used the augmentations in between and then tested it. So see, this was trained with the original data, no augmentation or no normalization of the images. You can see that if we have trained it on C3 center 3 data, we find that, so these are 5 different metrics: AUC, area under the curve, accuracy, precision, sensitivity, specificity. So you can see, for example, center 2 has very low AUC, accuracy is also low. When it comes to precision, both center 2 and center 4 have very low values. You can see here, right? So very low values of both. Sensitivity is also very small. So this was when it was trained on original data. When trained with the normalized data, not doing any augmentations, you can see immediately the scores improved. See, the accuracy goes from 28.1% to 85.4% immediately on center 2. And all sensitivity, everything actually rose above, and immediately the model came up with just normalization. And so there was not huge sort of calculations or computational complexity involved, because that algorithm was very clean, very small, that you just feed the data, it will simply do normalization within no time. Then we also trained with different types of augmentation and trained with augmentations as well as normalized data. Little bit differences it made, but we could have gone just with the normalized data. So with this, I'm not discouraging that we shouldn't use MLDL as a complete workflow, but the point of emphasis is, do we really need a complete MLDL pipeline everywhere? Maybe not everywhere. Maybe some parts we can do with the traditional small customized mathematical formulation pipelines and rest with the MLDL sort of a workflow. Testing generalizability, if you are young researchers, is really a key. I can collect my own in-house data, build all algorithms, do ablations and do extensive benchmarking, but still you need to convince the readers and the audience, bigger audience, that my model or the architecture that I have evolved is generalizable. So it is always good to demonstrate your technology on public data set as well as testing on different sites of data, which was the idea here, that we were testing on our own in-house collecting blood cancers data, but as well as we also demonstrated generalizability on different sites, public data set as well. I explained you that our data had label noise. So then comes the aspect, how do you handle the label noise? So that means, first of all, it should be handled in the training pipeline itself. I shouldn't be training my data where the label becomes a bit of a challenge, right? Somehow I should be able to find a strategy to remove at least those samples whose labels are dicey. So we did the classification, and it was again published in Medical Image Analysis Journal in 2021. So what we did was, during the training, we actually built two different, so this was the CNN, the first one was the CNN pipeline. So this convolutional neural network pipeline, which was extracting the features, and then we used different laws and projected for different laws in different ways, one with the global average pooling and another one with the flattened layer, and we used two different losses here. And then in a way, we are taking inference in two different ways on the same sample. And we said that if both the classifiers are saying with higher confidence that it belongs to this label class, then that means we are good to go, and I should keep it in the training data itself. But if there is a doubt and both have very low confidence, then we should discard it, at least not include in the training data. So in a way, label discarding should happen in the training data itself if there is it's a dicey label, and that's how we train. During the inference, then we use different technology. We said that I could think of label flipping, or I could think of sample discarding, that I would simply discard those samples and not make my inference on that. And maybe nowadays we talk about active learning, where you say that there is a human in the loop. Maybe that human should, or expert should, do the inferencing on that data. So we did that during the inference once the architectures was trained. But the idea is, if you understand that there could be a label noise in my data, the way it is being collected, take care of how you build the architecture so that in the training itself you can handle it, and while inferencing also, how do you want to handle it? Just take due care for that. If you build the technology that way, it would be really very, very helpful. So earlier we used to say in MLDL that we used to say two big threats: unsupervised learning and supervised learning. Unsupervised learning, for example, when we don't take cognizance of the labels and we don't say that you compute loss because the ground truth is given to you, etc. And supervised training, where you are, or learning, where you have the GT labels and you compute the loss with respect to the ground truth labels, etc. Now we talk about self and semi-supervised learning also. Why? Because we want to take or account for a lot of unlabeled data, unannotated data also in our training pipelines. So why it is helpful? If you particularly if you look at the medical data, expert annotations is always a big problem, right? So for example, if it is segmentation, I was showing you multiple myeloma slides. So if I need to do the ground truth labeling, so that means for segmentation, so that means the complete boundary of nucleus and cytoplasm need to be correctly mapped out. So it really took us a lot of effort. So every single slide was very large, 1536 into 2040 was a large slide, and one cell was roughly of the size of around 300 by 300 pixel wide. And then we were doing those annotations very carefully. One single pixel here and there will change your IOU when it comes to that. How come? Okay, so those sorts of annotation. So that is when we are doing the annotation. But when it comes to the expert annotations, for example, X-ray or maybe the medical images MRI, if you want them, or CT, that you want them to be segmenting or labeling the regions of interest, it is a big task to label the data. So lot of times we have a huge amount of unannotated, unlabeled data also on the global space, but a very small amount of annotated data. So we want to use both of them and have a pipeline where we can also ingest this unannotated data, but not by inferencing, but during the training itself. So this was another work that we did on segmentation itself, where we mix these different technologies. So for example, if you look at this, we took the mask RCNN architecture, and it was having, we used the ResNet 50 backbone. And so on the backbone, initially in the first stage, we trained it with the fully annotated data. Then in the second stage, we said that now we'll also incorporate the unlabeled data. So we did sort of self-supervised learning with the unannotated data. So here we use the Barlow twins model, where two architectures are roaming, same architectures, the backbones are shared. So you feed with the augmentations and you feed without augmentation. So this is the same image without augmentation, and this is the same image with augmentation. And here again, as I said, that we want to take care of how we do the augmentation. So we designed our own augmentation, which we said that generic domain aware, domain specific cell aware augmentation, where we did give different color contrast to the nucleus and different color contrast to the cytoplasm, as well as pasted some cells from one image to the background region of another image. That way we did the augmentation elaborately, and then we fed it to this self-supervised Barlow twins architecture, which works on the contrastive learning in the end and fine-tunes the backbone. So whatever was here, then we fine-tuned the backbone here, and then in the end we actually added both annotated as well as partially annotated data, and again fine-tuned. After 3 stages, we found that the architecture really worked very well. On this data, we had actually run the ISB 2021 challenge. On the leaderboard, the highest results that we were having was MIOU of mean intersection over union. IOU was around 93.81 or something. 3 teams which were at the top, all of them used very big, very deep architectures and used ensemble of those bigger architectures like VIT, etc. But our model was very small. So compared to the top performer, which was having 700 plus million parameters, our model was having only 45 million parameters and could match in the performance immediately on that, while using training on this architecture. And when we used little bit more number of parameters, it actually could beat by them by 2%, which was a huge jump, because all the teams were near about 93 point something after doing heavy ensembling and augmentation and everything with the deeper architectures, but we could meet that. So the idea is that if you can build your own customized architectures, understanding the problem, you can actually have smaller, elegant architectures, but you should be able to combine different technologies which are there in MLDL domain as of now. In another work, then we combine, now we say that sometimes if you, in the same architecture, you learn for multiple tasks, different tasks are looking for different features. So if one architecture is being used for multiple tasks in some ways, then maybe that feature learning becomes more robust and you find better performance to be coming out. So this was a paper in Mekai that we published, and here we actually built an architecture that could do all three: stain color normalization, cell segmentation, as well as cell classification. So you can see that there are two parallel pipelines running there. So this is sort of a unit kind of an architecture here in top and bottom. The decoder of features from decoder of one are being shared with the decoder of one are shared with the encoder of another one, and so on, vice versa. You can see these arrows going here and these going up there. So that was sort of feature sort of sharing that is happening. Then on the top, we are sort of saying it is identity, same image should come out, whereas on the bottom, we are saying that it is the augmented image, and here it should be the normalized image that should come out. So stain color normalization is happening. In between, we have put the classification head, so that is also doing the classification. So identity transformation, stain color normalization, classification, everything is happening in one. Encoder decoders are sharing the features, and that way. And then segmentation, instead of classification head, we put the segmentation heads, and we could see that it could do well on all these different types of tasks. So multitask learning is another really a key that you can actually incorporate. If you know that same data can be used for multiple tasks, it's actually good to build that sort of an architecture, because then the robust feature learning may happen and you find that the performance on all different tasks actually improve at the same time. So when we do research and we say that, oh, I have come up with 3 or 4 different types of novelty that I have added to my architecture, has it really worked? What has worked? So we always say, do extensive ablation, so that you can prove that what has worked, and you can yourself also figure out what is working in your whatever novelty you're introducing, is it really working or not. So the paper that I showed you on label handling, so we were doing the classification task of healthy versus cancer cell along with the label handling, and we had proposed an architecture where we were saying that there is a base architecture, then we were doing projection loss, we were learning class activation vectors, and then projecting data onto those class activation, and then had devised one different loss as well besides the cross entropy loss. So we were, so there we said that this is the base architecture over which the projection loss kind of architecture, whether it has worked or not, PRL. Then this is with the cross entropy loss, trained with cross entropy, trained with projection loss. Then we had actually used 2 classifiers in between and doing ensembling of that, whether that leg is working or not. Then label flipping, LF, or sample discarding, whether it is working, and what if we do all, then how does the performance comes out. So that is one key, that we did extensive ablation, and ablation is really important, we should be doing it. Another important thing is generally medical data is less. So compared to the bigger model, so saying that I'll do 80-20 split or 70-30 split is not a wise thing. You may find that the data variability, because the data is small, so maybe your training data has not captured, maybe has captured lot of nuances, but the test data is not representative of the training data. Moreover, you don't want to lose out on specific aspect of even one single sample. So we say do 5-fold cross validation. Even if the data was large here, we still did 5-fold cross validation, and we said that after we have trained 5 folds classifiers, we'll do the majority voting on the future or totally unseen test data. So besides splitting the data into, we first split the data into 2 parts. So one part we kept separately as a test unseen data. The other part that we took, we did 5-fold cross validation. and then built the different classifiers for one for each fold, and then did the majority voting. And that way you can sort of be sure of at least whatever data you have in sort of absorbed all the nuances of whatever data was available to you. Of course, the future data is not available to you, but at least you have done your best bet there. Then, where are we with reference to SOTA? So many a times as a young researcher, you will say, oh, I'll take so many up-to-date models are there on the net. How about I take all those models and start generating results with all those models, and I'm done and I'll present that. No, this is not how it should work. You should also look at what are the state-of-the-art architectures as of now. So if you are comparing with an architecture which is 3 years old back, the reader or the reviewer wouldn't be happy or excited about it, because every day the technology is changing, people are coming with better and better models, incorporating better things. So you should also be comparing, doing extensive benchmarking. So this paper was a bit old now, it is actually 2021. At that time, whatever were the state-of-the-art algorithms like ShuffleNet, GoogleNet, some smaller architectures, some bigger architectures, we compared with all of them. But at the same time, we also tabulated the number of parameters these models are having. So if you are building your own customized smaller architectures, so you can see that our model has still relatively much fewer parameters compared to rest. So if I see that the smallest model compared to these compared to our model were these two models, but then they had relatively much lower performance, around 7 to 8% lower performance compared to our model. So that means it is worth the effort. But rest of the models, although they were bigger in number of parameters, still our performance was better than them. Inference time, number of parameters, flops, etc., whatever your model is taking vis-a-vis whatever are this with the SOTA models, if you report them, that is always helpful. Now, again on another, this was sort of in the genomics area, where we were doing the task of novel miRNA, microRNA detection. Now this was the problem that I was saying, not everywhere ground truth is known. So if the genomics data is captured, no one knows what all miRNAs are present there. You will be going with the pipelines that are available, with which, because the data is huge, you will be matching, aligning, and then figuring out whatever miRNAs are, known miRNAs are there. So known miRNAs, that means whatever is available in the databases as of now, that this structure or this sequence, if it is found, I'll say that it is one miRNA that I have detected. Now, some miRNAs are detected, but some are still not detected. And in one data, no one knows which all are there present, because no human will go through that long, like billion long pair of nucleotide sequence and start matching because they have a structure or something like that. Alignment needs to happen and all those things need to happen. So that means that we don't know what all are there. We are going by the detection pipelines that are available with us. So if it is a novel miRNA detection, our problem was, how do we do the benchmarking? We didn't know how to do the benchmarking. So what we came up with the solution, we said, how about building a synthetic generator that generates known miRNAs as well as makes changes to the known miRNAs in such a fashion that the resulting sequence is also having the properties of an miRNA, so that it classifies as an miRNA, but is actually different from the known ones. So that I'll call as novel miRNA. And then once, because this is now what I have generated, so with the synthetic generator we'll generate that, and now we'll do the benchmarking of all the pipelines which are there, and then once we do the benchmarking, we'll know which algorithm is doing what task. So this is a typical problem that happens generally in the genomics area, that we just don't know which genes are the biomarkers, we just don't know which miRNAs or novel miRNAs which are not detected as of now are present in the data, and we somehow need to still work around and still come up with the findings, still need to do statistical validation, etc. So here also we did extensive benchmarking. After building our own simulator, we generated a lot of data and then did the benchmarking of the existing pipelines as well as our own customized pipeline, which we called as MIRPipe, and then did the benchmarking. But again, so this was how, if the ground truth was not there, we built a domain aware generative model of generating synthetic miRNA, novel miRNA as well as miRNA. We did that. Then in general, when you're building an architecture or a model, as I showed you with one previous example, that mix different technologies, semi-supervised, supervised. Here also we built a sort of risk predictor, where again we used all possible technologies like supervised and unsupervised. So how much time is left? I still want to track. 1 hour is done? 50 minutes left. So I explained the problem, and as a ML researcher, tell me how would you solve it. So the problem was that, so in cancer, for example, we do the risk staging. So this was again multiple myeloma, and the doctor gave us the problem that we'll give you the data. Can you do a better risk staging for us so that we know which are the low risk patient, which are medium risk, which are high risk? High risk means that the mortality may happen soon, and that means aggressive treatment is needed. Low risk means that we don't need to do much. We can just suggest them some medication and tell them to go, and we can as a follow-up, they will come at the regular intervals and so on. So if you are given this problem, how would you solve the problem? I hope, can I ask the questions in between? Okay, so how would you solve this problem? So don't look at my slide, just tell me if you are given a data, and it was a tabular data. So simple data, age, hemoglobin, albumin, calcium, EGFR, which is related to kidney, beta-2M. So that's all that they gave us, almost about 6 features they were given to us for all the patient. And if you are asked to do a 3-class staging, what will you do? Unsupervised learning? Yeah, clustering, right? Simple. You will do clustering, but then once you have done clustering, how would you figure out? 2 questions remain. How would you figure out that your clustering is better than the other ones, or is giving you better risk staging? And how would you validate that it is indeed a domain aware risk staging that should happen? You got my question? You have done clustering, you have generated, you are saying these are the 3 groups, I can do k-means, I can use Budge clustering, GMM clustering, tons of clustering algorithms are there, I can use them, everyone would cluster the data, but where is the GT? Where is the ground truth? That this is a low risk patient, this is a high risk patient, this is a medium risk patient. How would you then determine which clustering is really a better one? Huh? Pardon? Thresholds, but how would thresholds tell you? So data doesn't have ground truth labeling. You don't have ground truth labeling. I just gave you the data. These are the patient's data. Do something and give me a better algorithm that does low risk, medium risk, high risk stratification, and you should somehow convince me that you have done a good job.
Instead of doing a 3-class clustering, we do a K-class clustering, where we use as many clusters as needed to justify most of the variance, and then cherry pick a couple of examples in each cluster, ask the doctor, is this good, is this bad, and so on.
So I was given the problem of 3-class classification, and now I have increased the problem to multi-fold level by doing K-class, because now K becomes unknown. And then which one is really a high risk, low risk, I just don't have a clue still.
We cherry pick examples in every cluster.
But who would give you the cherry pick example that this is a high risk patient and this is a low risk patient?
Yes, so we do a 3-class classification on top of the T cluster.
There is no ground truth.
We ask the doctors.
Then now you're saying if there are 20,000 patients, you ask that person to probe. Now you label that this is a low risk and this is a high risk, would be a problem.
We have, say, 25 clusters. We've created 25 clusters. Now,
Won't work. It will terribly, I have made the problem very complicated. So simple solutions. One, I'll do clustering in varied ways, but again, will connect with the domain. That was the first thing I'm repeating since my first slide, connect with the domain. How to connect with the domain? I need to understand how doctors look at the risk staging. So there is a Cox proportional hazard model and there is a Kaplan-Meier survival sort of a test which happens in this domain. So if you have done software engineering, the reliability analysis is also one thing where the similar things happen. So one is that I look at the Cox proportional hazard model and look at every feature and see whether it is actually giving me which feature, where is the threshold, how it actually goes to the low risk and high risk. And little bit knowledge we understand from the domain and with the medical expert also. So for example, hemoglobin, if it is very low, it may become problem. So albumin or beta-2M maybe or EGFR may be working in a different way. If they are high, then they are hazardous. Hemoglobin, if it is low, then it is hazardous, and so on. So somewhere we need to see that. We did that. We first did the imputation of missing features, which will happen often in the tabular data. Then we did the train test split. We did k-means adaptive partitioning to figure out what is threshold for the feature where it becomes hazardous and where it remains normal, so that we can see the demarcation as two groups, that this feature, when it goes beyond this limit, it is going to the hazardous range and remaining as a low hazardous range. But how do we do that? So along with the data, we are also given with these 6 features, we are also given the feature of overall survival, how long the patient survived from the baseline when the cancer was detected first time, how long the patient survived when this test was done and these features were collected. So that survival data is there and who all collapsed, right? So who all died and who all are still surviving. So these two things, one is a threshold. So we figured out that the known thresholds which are there in the literature, compared to them, our thresholds are slightly different than the known thresholds which are there in the literature. Now this adds another nuance to the data. We generally say in medical data set, ethnicity makes a difference. So most of the models are actually on the Caucasian population, and that is why we found that when it is our data, we found that our thresholds were relatively different compared to the known thresholds which are there in the literature for that. So that was the first finding we found. Then what we did was that we looked at the domain and we found that Cox proportional hazard and Kaplan-Meier survival are the two tests that are generally done and seen in this domain. So we said that we'll look at the univariate Cox hazard analysis on individual parameters and then see the p-value or the threshold or the hazard ratio that it gives us, and according to the hazard we'll do the weighting of the different features and then do the clustering of that. So we build then the patient to patient adjacency matrix or the similarity matrix, because some patients might be similar to each other, they might be low risk, may be similar to each other, high risk may be similar to each other, and so on. So we built the adjacency or the similarity matrix and then did the clustering on that data. Once we did the clustering, we could see that it could cluster immediately. So my first bet would have been just do the k-means clustering on the original data. It didn't work. Nothing worked there, and it was still dicey that whatever we are doing is correct or not. Then we incorporated this domain knowledge and then built the adjacency with the weighted adjacency matrix, and then did the clustering on that. And once we did the clustering, still we didn't know how good it has done. Although we could now compute some other matrix of clustering, for example, concordance index, which says how much samples within each cluster are in accordance with each other and how much they different from different clusters. So you can compute those indices for the clustering data. In addition, what we did was that we then, because the features were only 6 features, we trained a J48 or a decision tree, because a decision tree on 6 features could easily work and could give us the rules. We trained this J48 decision tree on this and then looked at the rules and then showed it back to the doctor that these are the rules which are coming for the low risk, these are the rules which are coming for medium and high risk. Can you verify each of the legs? So for example, even in J48, I can actually have number of default parameters and I can have number of hyperparameters. I can adjust how much depth I can go, etc., etc. So we adjusted those hyperparameters number of times until the doctor was convinced that each leg, whichever is there in the decision tree, is now giving a correct interpretation. We actually stopped at that J48 tree, and then now we gave that model to them and also validated against the SOTA or the known risk staging methods whether it is doing a better job than them or not. So that's how we build the model, but then in the same model, we are using unsupervised as well as supervised model. We are using the domain knowledge so that we can pitch and we can convince the person that it's not just a method which is thrown, although you can see all these are not DL sort of a thing, they are very simple things, but still built connecting with the domain for which you are building the model. So ethnicity indeed matters, and then we built another calculator also. So this was, we called it as the risk calculator. So the first one was using simple features. We built another one where we actually we did clustering in multiple ways, we built multiple adjacencies, and then we called it as consensus based risk staging because we were building multiple adjacencies, then doing clustering and then taking the consensus and then build the J48 tree. In addition, we also used this time the genomic feature, high risk cytogenic abnormality, as a binary feature, and that further improved the performance and gave us one of the best performance on all the existing algorithms which were there. So this was one way of proving why should a clinician or a doctor should trust you, that you should somewhere incorporate interpretability of your model the way we built it with the J48 decision tree at the rule-based thing. In ECG data, we built our own algorithm, a DL, convolutional neural network based architecture. So the first model that we built, it was a 5-class classifier, and we wanted to show to the doctor why should a clinician trust that my model is correct. So for example, then we implemented the post hoc interpretability algorithm or deployed over top of that, which was the Shapley analysis. So how it worked out. So for example, look at this data. This was ECG is a 12-channel data. And generally the gold standard is that doctors collect it for 10-second duration. So for 10 seconds, so if the sampling rate of the machine is, let's say, 500 samples per second, so that means for 10 seconds you have roughly around 5,000 samples per channel. So you can actually put it in the Excel format also. So that means 5,000 cross 12 is the size of your data, whether you use it as an image or a matrix as an input to a 2-dimensional CNN or a 1-dimensional CNN. We designed a customized architecture because we said that it has temporal variation. So along the time axis, we should have 1D filters, and because the spatially also, that is these different channels also represent something, so we should also have a spatial filter also that works along the spatial direction. So we had 5 temporal layers, 1D CNN, 5 temporal layers and 1 spatial layer, and then we did the embedding, and it was a very small architecture that we also compared with the SOTA models. It really worked wonderfully, and then we wanted to do the post hoc explainability analysis. So this is the data which is of a person suffering with right bundle branch artifact, and in this what happens in the, this is the normal V2 lead, the first one. This is the normal V2 lead, this is how it looks like, this is a chest lead V2, and in this if it is right bundle branch block, so sometimes we get an additional peak here, you can see here, which we call as the M wave. So if there is an M wave, so if the cardiologist is looking at this ECG data, can immediately recognize that the person is suffering with right bundle branch block. Now the algorithm, it is saying it belongs to this class, but how do I make the clinician trust that my algorithm is not just randomly throwing out the answer, but is actually doing a good job. So we did the Shapley analysis on that, and we said that because Shapley is based on game theory, so if I say 5000 cross 12 becomes huge number of features, so we had to somehow decrease the number of top features. So we said that we'll look at the top 500 features. So whatever are the top 500 Shapley scores, wherever for whatever point we get a high value of Shap, that will label as important, and rest will label as not important. So this is a blue and red colored image that we have here. Blue means not important and red means it was important part of top 500 features. So this was the original data on which we analyzed, and this is the zoomed version of these 3 patches. So the red color pointer was actually placed exactly on this additional peak that we were getting in every beat. So that means indeed the model could figure out that here there is abnormality which was not part of something which was not normal, based on which I am saying that this is a diseased kind of a ECG, and that's how I am interpreting this. So again, you go to any domain, every domain has its own nuances. In healthcare, it is life of a patient, so you need to be doing correct diagnostics. So that means you should make take clinicians on board with your post hoc interpretability analysis. Indeed, whatever algorithm is giving you is correct. In addition, rigorous statistical analysis should also be the key, shouldn't be ignored out. Even in ML-DL results, now in ML results, you should be reporting confidence intervals, you should be doing all statistical analysis, and even otherwise. So for example, in the stain color normalization paper, we did lot of extensive statistical analysis we used, but you need to see which statistical test is applicable to your data. So for example, there we had we were doing that this method is working better or this method is working better, and we were computing some numbers. So maybe the RMSE, etc., and so on different images we were doing that. So we built, so for example, t-test, we did t-test or Wilcoxon sign rank test, provided the assumptions of those statistical tests are met. So rigorous statistical analysis is also important when you analyze your data. So this is another framework where we worked on EEG data. Now, why this is important? So for example, here we were working with the problem of classification. We were working actually, we approached one school where they had subjects of intellectually development disorder, basically autism of different range. And now we wanted to see how brain networks are different in the data of these different healthy versus this class. So we wanted to collect their EEG data, but there was a challenge. Collecting EEG data was not easy because some subjects are very hyperactive. Autism is of spectral disorder, so some are very hyperactive, and they wouldn't accept that. So we wanted to collect with the emotive data set, which actually is a kind of a headset. You can put it on the top and then you can collect the data. So they will go restless. So what we did was we 3D printed the sort of emotive type of headset. Then we made them accustomed to that under care of their tutors, whosoever were their caretakers, secondary caretakers or class tutors. So we made them accustomed to wearing them. Then we also, so the school was playing music on regular basis for those students. So those musics were played while they were wearing the headset, so that way they were made accustomed to that. And then we collected data. Now see, the amount of data collected was very small. 7 healthy subjects and 7 subjects which are with this disorder. Now if I build any method and I say that the functional networks under music of the two groups are very different, brain networks are very different, how do I convince the readers that it is indeed different, right? So what we again resorted to the rigorous statistical analysis, and we made use of permutation testing as a framework in this, where we said that these are two groups of people, and we made the brain networks and we collected data, made brain networks, or the way we were collecting the data, analyzing the data, into dividing them into different spectral alpha, beta, gamma, delta rhythms of that. And then we said that we'll swap one subject randomly in the two groups. So when the two groups are absolutely separate, then we'll look at the features, and then we'll randomly swap subjects here and there. That we call as the null hypothesis, as a different one, because then I'm doing the mixing, and that way I can generate huge amount of data. So we say that we generate data under null hypothesis of feature, maybe the degree, etc., or anything, and then a feature when the groups were intact, and then did the permutation testing framework, and then proved that indeed whatever we are getting as the different brain networks, they were really different. So that means that statistical analysis or statistical frameworks can really come very handy to you when the data sets are very small, and you can still prove with great accuracies that whatever you have done is correct. So now sort of little bit nuance I have given you, but there are still lot of, like, there are possibilities of innovations and opportunities in healthcare. So for example, building foundational models, which is what we are headed towards. On the fly fine tuning of models. So if you have built a model and deployed in a hospital, no hospital would like to share the data, or you still want to improve the model as the prospective data comes out. So one is that, for example, in GPT, etc., you have also seen that they use our data the way we use it, and they use the data after every 1 month, 2 months, they are fine tuning the model. So on the fly fine tuning of model should happen. That is how you should deploy them. Federated learning can also be used where they don't need to share the data, but they can share the weights to the central server, and now you can update the model and then deploy, although it also, the area itself is a big area, because someone can also start corrupting your models or can start stealing your data. So newer architectures are coming. LLM based inferencing, now agentic AI is also coming as a big way, and we can build agents that do different tasks and build a complete agentic pipeline that can do out of distribution detection. That can also become one of the big problems in the, and becomes a big problem in the medical data, how you handle it. Counterfactual analysis, particularly helpful when you're doing treatment analysis. So you can give only one treatment to a patient, but you would also might be interested in how the patient would have responded if I had given this treatment. Now that means you're not giving that treatment, but you would like to do that counterfactual sort of analysis. So this is where you do now random control trials, which are very expensive and difficult and long time lasting, whereas compared to that, if you do counterfactual analysis, then maybe it can shorten the pipeline of drug discovery, etc. So then digital twins in healthcare, again coming a big way, that you can actually have a digital twin and then do all sorts of experimentations and do that. Use of metadata with the advanced models. So that means that now not only I can build a model on imaging data, but if I have lot of other laboratory, clinical, demographic and other data as well, then we can incorporate them. Comorbidity data, so we can incorporate them to do enhanced analysis and build robust models. So that way, electronic health record integration or longitudinal data analysis with them is the key that you can really do a lot. Drug discovery, drug repurposing are big areas that are coming up and that are really helpful in the medical domain. Current problem of importance is also global antimicrobial resistance. You might be hearing it so often that people are actively working, and WHO is also keenly looking at this as a bigger problem to be solved. Then augmented reality, virtual reality applications, which are really helpful in, for example, interventional studies and medical interventions where you can actually help cure people, can really do, and many, many more things to go there. So other challenges, technical challenges, economical regulation issues, ethical issues in AI, they are still there that you need to deal with them. So that is all. I would like to acknowledge all my funders over years, all my collaborators, and many UG undergraduate and postgraduate students at IIIT Delhi, and in general support of IIIT Delhi, for example, Infosys Center for AI, as well as Center of Excellence in Healthcare, as well as the complete supportive staff who have helped us over years. This is my lab. Currently, I have 7 PhD students in my lab who are working on different areas, although number of students are contributing in different ways. Thank you. Questions? I would be happy to take the questions.
So, thank you, ma'am, for your amazing lecture. And I had a question that fMRI signal is very expensive, right? So, can we use EEG signal to predict fMRI activation maps?
So good question. We generally say that there are different modalities. EEG is very good in temporal resolution. fMRI is very good in spatial resolution, the way 3D structures are there, right? And you can analyze. So now you're saying, can I do the same inferencing as we do in fMRI? If you ask my personal opinion, I would say EEG data is very rich, low cost modality. We should be able to do whatever it is possible through EEG data itself. It's a rich modality, provided we build very strong algorithms and architectures on analyzing the data. fMRI is good, but we initially worked in first 3 years on fMRI, but over years then I moved to EEG data. I would still like to see EEG data going big way compared to fMRI.
Thank you, ma'am. And another question I had was, there are so many US or developed countries data sets, right? But on developing countries,
which data?
Any data we look, there are mainly developed countries data set, right? But in developing countries, there is still a hesitation to give data set, and how can we approach to that problem, and how can we use existing US data set to generalize to developing countries?
Okay, good question. So this is true that, for example, when we talk about developed countries, they actually implemented their electronic health record integration and everything much earlier than most of the developing countries. So their data is well structured. They have good government protocols to anonymize the data, put in the central repositories, and there are strict guidelines on sharing the data. So examples are, for example, over dbGaP you can see a lot of medical data sets. Likewise, UK Biobank are big data sets. So these developed countries have lots of data, but they have also put in place the guidelines for accessing those data sets. They are given with controlled access that you can utilize those data. When it comes to developing countries, we still need to we are evolving those guidelines. For example, India is now making huge efforts. We have started making the centralized repositories where government is coming with the guidelines where we are now have started depositing the data. I know about Brazil is also doing a lot in this area. They have already started building big data sets and centralized data sets, anonymized data sets. So I guess we are making efforts, but as of now, we can use all the data, whatever is available. So for example, when we are building the models, we are using the in-house data set. They might be small, but still we can do inferencing on them. At the same time, we are also making use of the available data sets in the public spaces. We sort of scrape those, curate those, and then use them. At the same time, wherever the controlled access is there, we try to access those data and then build the algorithm. So same thing can be done by you as well.
So you said that ethnicity can really affect prediction and all, right? But my question again was, how can we use US or the other data sets to deploy models and make it work in other ethnicities?
So you cannot just arbitrarily use their models, the models built on their data, just deploy it that way. But what you need to do is that you need to look at their data as well as have your own small data, build an architecture that incorporates that ethnicity, and but is also being benefited by the large amount of other data as well. So the way I was saying that there is a huge amount of unannotated data, semi-supervised learning. We are self-supervised. We are making use of unannotated data as well. So same way you can do large amount of other ethnicity data, small amount of your ethnicity data, but still you are benefited while building the model, that the model extracts the relevant features. It is only the cutoffs that are slightly varying. You can make the model in such a fashion that it also accounts for that ethnicity within the model and then build a robust model. So you will definitely be still benefited by the large amount of data. But don't deploy the model blindly. That's the take home message.
Thank you, ma'am.
Hello.
Mm-hmm.
So thank you, ma'am, for your wonderful talk. So I have very basic question to ask you. So from a clinician perspective, so if we have some specific data and we want to make a clean level data out of it, so how can we start? So that it supplements us as a scientist and other people who want to do the research in that data as well.
So I haven't understood the question properly. So you are saying, how do I clean the data?
Yeah, starting with like if I have a raw data, how do I make it presentable so that people who want to do the analysis can work on it?
So that goes with the domain, like what kind of corruption is there in the data. So so data curation is the key to success in ML. So many a times I see that students would take the data and would start throwing the algorithm, and I would ask, like, have you seen every image or every sample in the data? Is it really correct? So I give you one example. We were working on EEG data and we had small subjects data. It was on virtual reality, etc. So we were looking at that sort of application. And we realized that we are not getting the desired result as was expected of the data. Then after some time we said, let's look at the data. Now EEG data is also multi-channel data. You are putting sensors at different regions on the cortex and then you are collecting the data. We found that out of 20 subjects data, only 6 subjects data was absolutely clean. On other 14 subjects data, either 1 or 2 channels or some channels were dropped, means were dead, there was no signal. Or in some channels of some data, it was pure sinusoidal noise. So that meant it was the power line signal that was there. Now, if I don't see the data, that means I'll start building the algorithm. I may actually spend 6 months, 1 year, throwing huge amount of data, but still not getting desired result. Why? Because I never curated my data, didn't see the data. So whenever students are working on imaging data, I say that visualize the data. If it is ECG, EEG data, just pass through your eye. Artificial intelligence means that it has to work with the intelligence that you have, right? But it has to imbibe that. So how do you imbibe that? You need to curate the data. But how would you curate the data? You would curate the data on the problems that you see on the data. You can't just blindly curate the data as well. If I understand that my some channels are dead or some channels are having power line interference, maybe I wouldn't like to lose out the subject, but what I would like to do is, maybe I would like to interpolate those channels data with the neighboring regions, spatial regions data, and then curate the data and then put it out there. If it is noisy, I would like to remove that noise and then put it there, curate the data, and then put it in the open space. So there is no standard way to curate the data. You need to first understand what problems it is suffering with, then clean the data, then put it out in a format that can be usable by everyone in the community. Hope I have answered the question.
Yeah, thank you. Thank you, ma'am, for the lecture. My question was on the level noise. For example, if you detect cancer in certain patient and when you provide chemo, the level of the distribution goes towards the normal distribution. And how do you detect when to stop giving the chemo?
No, no, that is the clinical decision. That won't be my decision, that would be the clinical decision. A clinician would be taking a call whether the cancer has subsided or not. I was giving you the example that when we are looking at the data and how the clinicians are making those, they're doing the specialized test like flow cytometry analysis or mass cytometry to take a call whether the cancer has subsided. So it is their decision. But we wanted to understand that, incorporate that knowledge and somehow imbibe that knowledge to build our model that actually works.
So why can't we incorporate those psychometric tests in the model itself?
And then I need to work on the cytometry data. But cytometry is an advanced test. It's a costly test. So I would like to do with the imaging, microscopic imaging, every path lab is making that slide and can scan it and then do the inferencing. If I have to do the cytometry, then I need to have, so one test that would cost me now 50 rupees, I am then spending 10,000 rupees, and then also a big machine which is very expensive, I need to buy that. Why do I? That's what this AI ML is all about, that we should make the technology affordable and usable by all. The test should be available at all the centers everywhere, right? That's the idea. Of course, cytometry data analysis is also being done with MLDL, but for different uses, right?
Thanks for the session. I actually have a simple question. So as I was looking at the one slide images that you were showing, so did you actually do something about the variability due to the devices, like capturing devices?
So I showed you one result where the data was collected from 5 different centers. So assuming that those centers might be using different slide scanners as well.
Yeah, I mean that if you've got a different device, then maybe the artifacts will be different as well. So
yeah, that's what. So once the data comes, you're incorporating all knowledge into that and then making a model which is a generalizable model. That's why we trained on one center data, tested on different center data. If it is working, that means it is invariant to the device, and as well as artifacts are natural to the application.
so in a way, the five-fold cross-validation would be
5-fold cross-validation on the training data is separate from saying that I'll train on one center data and test on another center data. That is different. So two things are mixed up. So maybe we can connect over tea or lunch and then I can explain that.
The other question I have is, you proposed the geometry-inspired chemical addition variant state normalization model. So as you were comparing to the baseline models, I noticed that the baseline models actually did not use the state normalizations and the techniques used to process the data. So how would those both baseline models compare to yours if you added the processing techniques into those baseline models as well?
Good question. So the problem was something else. So we didn't want to build an MLDL model. So what I showed you, that what if I make a mathematical, like use the math to build a model instead of doing an MLDL sort of a thing. So geometry inspired, it was using SVD and all that, and we did the stain color normalization. But when we tested it against the baseline, so that table had all the results. With the MLDL model, trained without on the original data, trained with only augmented data, trained with only normalized data with our algorithm, trained with normalized as well as augmented data, and what are the results and how it goes. That is the best ablation we could do.
And my last question is, I'm unfamiliar with the idea of permutation testing frameworks for small data sets. So my understanding is that you use this for like super small data sets where t-tests would be applicable. And if there's like a bias in the data set, wouldn't that like grow as you're doing permutation testing?
So you're saying CNNs would become a problem with the bias?
No, I'm saying that the data set itself would not be very representative of the population that you're trying to model or something like that.
So it's always the case. Medical data sets are small, however large you collect. It will never be representative of the entire population. So still, you would like to build the model with whatever data you have, and that's why when we are building the model, we are also trying to look at what all publicly available data sets are there. So for example, for cancer risk staging, it was 1,000 patients data that we had, but 1,000 patients data was also available at Multiple Myeloma Research Foundation through dbGaP, which is maintained by in US dataset repository. So I'll make use of all the data, but at the same time, in the end, I'll do post hoc interpretability analysis that will tell me how good my model is, whether it is really capturing the nuances of the data or not. That's the best we can do.
Thanks, ma'am.
Thank you. Any more questions? I am happy that you guys asked me so many questions, means I could connect with you. Thank you so much.